Hi, everybody. So today we're going to be looking at some new stuff, probably new to a lot of you, drawing chemical structures, and then more specifically, drawing them in the particular way that allows us to more easily communicate organic molecules. Now, when we talk about organic chemistry, you've probably heard that term before. There's courses on it and such. But what we're really talking about is carbon-based chemicals, things that originally were thought to only be able to come from living things. Now we know that's not true. Chemicals are chemicals regardless of where they come from, but that's where that name comes from. And these are chemicals that are most commonly seen in biological systems. So when we get more into things like biomolecules, macromolecules, carbohydrates, proteins, stuff like that, that's all organic molecules. This is also where we'll see things like pharmaceuticals and drug structures. So a big portion of the chemistry that we're going to be discussing this semester is dealing with organic chemistry, organic chemical structures. And so that's why today we're going to focus on drawing those. All right. So there are a couple documents to get you started and to give you some practice on Blackboard. But if you have no experience with this stuff, that might be a little tough to jump straight into. So that's why I want to give you a little background and a little context before we get into actually doing that on your own. All right. So first, we have to talk about the most basic, easiest to draw structures that we call Lewis structures, named after somebody who first developed them. And Lewis structures are things that look like this. So you've probably seen something like this before, even if you haven't had to draw them yourself, where you take the atoms and you connect the different atoms with lines, and the atoms are all expressed by their chemical symbols from the periodic table. So this one is a molecule of carbon connected to hydrogens with these lines. And you did something like this in one of the activities last module, right? When you had to draw those water molecules and kind of like take apart those ball and stick models. So this is called a Lewis structure. And that is a representation of this molecular formula. So that's a Lewis structure. This thing is called a molecular formula. All right. So now first we're going to talk about how do we know that this structure can be expressed in this way and it's not like something else. Like if we saw CH4, why can't we just write down, like, how do we know that this isn't the way that these things are connected? How do we know that it's actually connected this way? And there's various theory behind this that we're going to get into a little bit maybe later in the class, but not a ton. The nice thing about organic molecules, actually, let me leave that there. The nice thing about organic molecules is structurally they're pretty predictable. So if you look at the whole periodic table, there's all these elements and they all have these different ways of bonding in different situations. But when we stick to the organic molecules, which means we're sticking to primarily this kind of upper right area of the periodic table, so carbon, nitrogen, oxygen, and then the halogens, this column here, fluorine, chlorine, bromine, iodine, and then hydrogen way over there is also going to be in our structures. But we're going to mostly ignore kind of this bottom area. We're going to mostly ignore back here all these metals and stuff because metals bond and behave chemically in a different way, and so that's not that doesn't concern us as much for this part, for these types of structures. So these are fairly predictable. So what we can do, instead of going through the chemistry and trying to like derive all these rules, I can just tell you the rules. And as you use them over and over, you'll find them pretty basic. So by rules, I mean that certain elements tend to bond in a predictable manner. So for example, carbon generally makes 4 bonds to other atoms. Now, these aren't absolute rules. Nothing's ever absolute in chemistry. There's always exceptions. There's always weird situations. But for our purposes, for what we want to be able to do with this stuff, that works. And we can kind of just remember, okay, whenever I have a C atom, I got to make sure there's 4 lines coming off of it. Again, not always, but for what we're going to see, that's going to work. Hydrogen, we're going to see generally is going to make one bond. All right. So yes, there's exceptions. Yes, there's unusual molecules where that's not true. But for what we're going to see, we can say that's pretty true. So using those two rules then and going back up to our structures, we can see why this is the correct structure and this one is not. Because in the structure on the left, we see carbon with 4 connections to other atoms. So that follows this first rule. And we see hydrogen with 1 connection to another atom, which follows the second rule. In the second structure, we don't see that. We have carbon with only 1 bond, only 1 connection here. And we have hydrogen with 2 bonds, several hydrogens with only 2 bonds. So we see how this structure violates the rules and therefore is not a reasonable chemical structure for these atoms. Now, a couple others that we're going to see. Oxygen. Generally going to make 2. Nitrogen is generally going to make 3. And the halogens, sorry, it's too low. The halogens, so that's F, Cl, Br, and I, generally are going to make 1 bond like hydrogen. All right. Now, some of these rules are more absolute than others. So for example, hydrogen almost always makes 1 bond, except for just a couple very strange exceptions. Nitrogen is a little more like, yes, it generally makes 3 bonds, but there's plenty of structures where it has 4. So that's a little bit less absolute. But again, these are a good starting point to how you can draw these structures and at least propose reasonable structures. So let's use these rules for a little bit more complicated of a structure and see what we can put together here. So let's say we have a molecular formula C4H8O. All right, we want to put this together. So that's our molecular formula. That tells us how many of each type of atom is in the structure. So let's start putting it out. Now, we can start connecting this however you want. In class, if we were doing this, we would be using actual molecular models and we would be like putting the pieces together. At home, we don't have this, so we'll be doing it on paper. But what we can start doing is just connecting some stuff together and kind of seeing where it takes us. So we know we're going to start from either the carbons or the oxygens because hydrogens only can make 1 bond. So we got to kind of wait and put those around the outside because those can't ever go in the inside of a structure because they can only connect to one thing. So let's start with the carbons and just start putting things together and see where we go. So I'm going to put my 4 carbons in a line like this. I don't have to put them in a line. I could make one coming off this way. That would be fine. As we'll see, there are lots of different correct answers here. This molecular formula is not specific enough to tell us exactly how all the atoms are connected. It only tells us how many of each atom. So what we're going to do instead is just kind of start pushing these other things around and see where that gets us. So maybe we can put the O over here. And now we have 8 hydrogens. So we'll start putting those around. 1, 2, 3, 4, 5, 6, 7, 8. Now that's our molecular formula. We can't add any more atoms to this structure. And hopefully you see a problem here in that this carbon right here only has 3 bonds and this oxygen only has 1 bond. So that violates our rules here. And so this is not a reasonable structure for C4H8O because the carbon and the oxygen don't have enough bonds. These do, but these don't. Now, if you've taken other chemistry in the past, you may have heard something called the octet rule. You can use all those skills you've learned before. You'll get these structures. Also, this is this is just a way that is specific to organic molecules that makes it a little easier. All right. So what do? How do we solve this problem? We can't add any more atoms, but what we can add is more bonds. So one way we can do this is we can put what's called a double bond between carbon and oxygen. Now, we haven't gone through the background of all this, but these bonds are shared electrons. They're electrons that are shared between the atoms. So when we put an extra bond, all we're doing is we're saying that these two atoms are going to share another pair of electrons. And by doing that, we can see that that solves our problem. Now carbon has 1, 2, 3, 4 bonds, so that's good. And oxygen has 1, 2 bonds. All right, so this becomes a reasonable structure for C4H8O. Now, there are lots of different ways to draw a structure that is C4H8O. Any way you can do it that follows these rules is fine. So, for example, here's another one. So in this case, I've actually connected them in a ring. But you'll notice I still have 4 carbons, 8 hydrogens, and 1 oxygen. So it's a good structure. So take a minute now, or if you're watching live, you can do this later. But give yourself a challenge and see how many different structures you can come up with that are all C4H8O. These, by the way, the name that's given to different structures that have the same chemical formula are called isomers. So you should be able to draw many, many different isomers of C4H8O, all kinds of different structures that have that formula. All right, so that's Lewis structures. Now what happens is, as the molecules get bigger and bigger, you can imagine this becomes a little bit tedious. You have to draw in every carbon and every hydrogen coming off. And if you had like 10 carbons and 20 hydrogens, let's say, that's going to start to be a pretty big job to draw every single one of those things. So over the years, chemists have come up with some various shortcuts that still allow us to communicate all the information we need, but in a little bit more abbreviated fashion, so a shorter fashion. And so that's where we get some of these other types of structures that you see in the handouts or in the the downloads on Blackboard. So let's talk about those now. So what we're going to do, I'm going to make a little table here of some of these different types of structures. And we're going to look at how we can interrelate and kind of go back and forth between them. So the first one is the one that we've been talking about, Lewis structures. There's another type of a structure called a condensed structure. And then there's a third type that we're going to call a line structure or a skeletal structure. Different books, different references refer to these in different ways, but line structure, skeletal structure, something like that. That's what we're talking about there. So these go from kind of least to most abbreviated. So a Lewis structure is fully non-abbreviated. Everything is drawn out. And then we have a condensed structure where it's slightly condensed. And then we have a line structure where it's very condensed. So let's take some molecules and kind of show how this works. So our first one, we're going to take a molecule called propane, which is C3H8. And we're going to draw out a Lewis structure like this. I left myself a little bit more room, but you can see that. Okay, so C3H8, 3 carbons and 8 hydrogens. And the Lewis structure, the carbons are kind of in the middle and the hydrogens are drawn off there. Now, if we were doing this with models, another thing that you would notice is that real molecules don't have 90-degree bond angles like that. They're not in a straight grid. They actually kind of zigzag. And we'll use that a little bit later. All right, so let's say we didn't want to have to draw all this out all the time. One way that we can make this a little faster is to draw what's called a condensed structure. And in a condensed structure, we take all these hydrogens around the outsides of these carbon atoms and we condense them down onto the atoms themselves. So there's 2 different ways to draw a condensed structure. One way is to condense those hydrogens down onto the carbons, but then still draw lines in between the carbons. All right, so this is an example of a condensed structure. Now, what's important to know about this is the hydrogens are not in between the carbons here. Even though we draw them like this, we have to understand that the hydrogens are actually around the carbons. And the way that we understand this, or the way that we can always check this, is by, again, remembering the rules and knowing that carbon needs 4 bonds and hydrogen needs 1 bond. And if we tried to put hydrogens in between the carbons, we would violate those rules. Another way to do a condensed structure is to get rid of these lines entirely and just kind of mush everything up against each other like that. This is extremely useful for things like typing. Imagine if you wanted to put a chemical structure into Microsoft Word or something. It's very difficult to try to get all those lines to line up properly, but it's pretty easy to just type this and do a couple subscripts. So that's a nice way of communicating information just in one typing line. All right, and then our final way of expressing these structures, the line structure, is going to look very, very different. It looks like this. That's it. That's the whole thing. Right. So one way that we can kind of keep track of this and start talking about how this works is by labeling our carbons. So I'm just going to call these 1, 2, and 3 over here on the left. And then over here, you can see how those correspond to 1, 2, and 3 here, 1, 2, and 3 there. And then over here, you may be able to guess that that's also going to correspond to 1, 2, 3 there. Now, these line structures take advantage of the fact that the rules work so nicely. And the way that the line structures work is that we have carbon atoms anytime there is an end of a line or 2 lines come together. So that's a couple of ways to express that. One is we have to use zigzag now, because a straight line, you would never know where 2 straight lines come together because it would just look like a line. So we use a zigzag instead. It doesn't matter if it zags up or down or sideways or whatever, but anytime lines come together, we know there's a carbon atom there. We can also draw more lines branching off depending on the complexity of the structure, which we'll get to in a little bit. So that makes a really nice, quick, easy visual view of how the carbon atoms are connected. Now, how come all the hydrogen atoms are gone? Well, the hydrogen atoms are gone because, based on the rules, we don't actually need to show them. We know carbon has to have 4 bonds, and we know hydrogen makes only 1. So if we show, let's say, for example, carbon 1 here has 1 bond shown, we know from the rules that there has to be 3 more there somewhere. And since they're not shown here, we can assume those 3 more are hydrogens. So one way we can word that is we can say that we assume enough hydrogen to make 4 bonds to each carbon. All right. So let's try this a little bit more. We're going to use the same table format, and we're going to slowly build up our complexity of structures. Let's take one like this. Oops, that's already getting to the condensed structures. Pretty soon we'll be able to leave the Lewis structures behind and just deal with the condensed and the line structures. Let's say we have a structure that looks something like this with a double bond. Whoops, there would be no hydrogen there because that carbon already has 4 bonds. Okay, let's say we have something like that. So there's our Lewis structure. It's all drawn out properly. Now let's say we want to express this as a condensed structure. Now we have some choices here, and some of them are going to be a little bit easier to see than others. All right, so the easiest way to draw a condensed structure always is to leave the lines between the carbons intact. So leave the bonding between the carbons as is and just condense the hydrogens down. So like we can see there are 3 hydrogens on this carbon. So we can just make that one a CH3. And then we can move over to the next one. This is connected to a carbon that has no hydrogens on it. So that just stays C. Then we're going to double bond over to this carbon that has 2 hydrogens on it. So that's CH2. And then this one's going to come down here to another CH3. All right. So that's a nice condensed structure. And this is definitely my favorite way of drawing condensed structures. It's very clear. It still abbreviates the hydrogens, and you know how everything's connected. Now, if you notice in the homework in the packet, they even go one step further, and they want to talk about how to express this on just one line. So let's talk about that. If we only want a condensed structure on one line, then we have to deal with this idea that this thing like branches off that second carbon. So let's label our carbons again just to keep track of everything. We'll just call them 1, 2, 3, and 4. 1, 2, 3, 4. And then let's talk about how we can show this branching off on just one line. The way we do that is with parentheses. So a couple ways we can do this. One is we can notice that this carbon actually has 2 different CH3s connected to it, 1 and 4. So one way that we can draw this on one line is to put those 2 in parentheses. Say CH3 taken twice. There's 2 of them. Those are both connected to the C number 2. And then that's going to be connected to the CH2 on one line. So just to keep track of everything, this is carbons 1 and 4 are these over here. This is carbon 2, and then this is carbon 3. So this is a pretty big abbreviation. We have to know some chemistry to be able to decode this, because we have to know, first of all, that those 2 CH3s are actually distinct and not connected to each other. Having them taken twice like this kind of makes it look like they're connected to each other. Now, how do we know they're not connected to each other? Well, we can try it and see. If we draw CH3, CH3 like that, and then CH2, we can see that this carbon has too many bonds because it has 3 hydrogens connected and then 2 carbons also. So that's 5 total bonds. So that doesn't work. And then also we can see that this carbon only has 2 bonds. And even if we were to put in the double bond over here, it would still only have 3. So that when you get something like this where it doesn't seem to work out when you try to connect it, that's a clue that something is wrong, that you've got it connected in the wrong way, and you have to kind of rearrange things. So that's how you show that these in the parentheses are actually 2 separate ones, because we have to know that a CH3, a carbon with 3 hydrogens, could only ever be connected to one other thing, because only 4 bonds total on carbon. So that's how that works. All right, so this doesn't work. We can erase this. Now, to make things a little bit more clear, maybe, and still on one line, so this is how the book does it, and how you'll do it in the homework. Another way you might see it is you could still go in a linear way from left to right, and when you see something branching off of something else, you could put that in parentheses. So you could go CH3C, and then put the other CH3 in parentheses, and then CH2. That's also a correct way of drawing a condensed structure. So now we have here 1, 2, this is carbon 4 coming off of carbon of this one here, and then this is carbon 3. So these are all correct. These are all correct condensed structures. All right. So now moving over to the line structures. When we draw a line structure, we have to do this zigzag thing, and we have to make sure that we're accounting for all of the carbons where we're zigging and zagging. So this one would look something like this. Let's label those carbons again and then talk about how we got there. So this would be carbon 1 over here, carbon 2 in the middle, carbon 3 over there, and then carbon 4 down here. You can see the double bond here. Double bond's really important to show in a line structure because if we didn't have the double bond, then we would be assuming 3 hydrogens on this carbon and one hydrogen on this one instead of 2 and 0. If we look at this structure now, we can tell how many carbons and how many hydrogens are there. We've got 1, 2, 3, 4 carbons. And then our hydrogens, we have to look at each one and say, okay, well, this carbon 1 has 3 hydrogens connected. Carbon 2 has 0 because it already has 4 bonds. Remember, I'm counting up to 4. I'm putting in enough hydrogens to get up to 4. This one, 1, 2, and 3. And then this one, 1, 2. All right, that works. Now, in terms of how to actually draw that, just a couple considerations here. So first of all, what if we started with a zigzag this way? Which I said is fine, right? You can start your zigs and zags any way you want. Let's say we did this. And then we recognized, okay, I've got that. That's going to be my carbon 1, 2, and 3. And then I'm going to put my double bond between 2 and 3. And then where do I put my carbon 4? Now, because of how the condensed structure is drawn over here, we may want to put carbon 4 down. But we don't actually do that. We put it the other direction. And the reason is that you would see this if we had the models, but chemical structures have pretty fixed and standard bond angles between them. So if you were to actually look at this structure, like a physical model of it, you would see that you couldn't actually squish those carbon atoms together that much. They'd want to be spread out. So a good rule of thumb is just always spread out the angles as much as you can. And they'll kind of usually look at these kind of tripod shapes. If you have 4 things connected, you'll get like this kind of a shape, something like that, where oops, sorry, you can't see that. That kind of a shape where everything's pretty spread out. Just kind of try to spread the bonds out as much as you can. I wouldn't say that it's wrong if you put it this way, but you wouldn't see it that way. All right, so that's the basic idea. Let's practice this a little bit more with, let's add some other atoms in now. So let's start looking back at some of these structures that we did before. Up here, these C4H8O isomers. So if you were able to either pause the video or just later draw a bunch of C4H8O isomers, one thing you might want to then try to do is see if you can convert them into line structures and check that they are indeed still C4H8O. All right, so let's draw some C4H8Os, and we'll start with the ones that we already drew. So we've got this one. Remember, we had to put a double bond in there to make sure that we had enough bonds for the carbons. All right, and then we're going to draw this in a condensed form. That's going to look like CH3, CH2, CH2, CH, then O, like that. Now, as I've been doing, you'll notice that I always like to draw the condensed form with the lines connecting the carbons. I just think it's easier to see that way, especially when we start putting it into the line structures. But you can also just squish all that together and just write CH3, CH2, CH2, CHO. And just leave it like that with no lines at all. All right, I'm going to leave this like this. And then let's draw our line structure. So when I want to draw a line structure of something like this, I'm going to count up how many carbons I need and then start drawing them out. So I've got 1. Remember that 1 is right where you put your pencil down, not where you draw it 2. As soon as you draw a line, you've got 2 carbons, 1 on each side of the line. So I'm going to go 1, 2, 3, 4. And then I've got my double bond to oxygen. And that's it, because I don't have any other double bonds. and I don't draw in the hydrogens that are connected to carbons. Okay, let's try our other C4H8O isomer that we made, which had them all connected in a ring. Again, as usual, let me know if you have any questions in the chat, or if you want me to slow down or go back and explain other things. So a ring structure like this, when we draw a condensed structure, I would say, I think there are ways to do it, but I would say the easiest and most clear way is, again, to leave the shape intact and just condense the hydrogens down. So we might draw that like this, CH2O. Everything here is a CH2, actually, because there's 2 hydrogens on each carbon. Oops. Okay. All right, so I might draw it like that. And then for a line structure here, we're actually going to keep that same shape, but because we're only drawing lines, we actually just get a nice pentagon structure with an oxygen there. So we might have a line structure like that. Again, we have our 4 carbons, and each one is going to have 2 hydrogens. Okay, let's take a look at the one of the documents on Blackboard. This is where all of your homework for this section is going to come from. It's just a little excerpt from a book that gives you some more examples on how to expand these condensed structures with the parentheses like we just talked about. So first, it's going to talk to you about turning the condensed structures into the Lewis structures, and then it gets into these line structures. So you can imagine a big molecule like amoxicillin here, which is an antibiotic. To draw it out as a Lewis structure is cumbersome. There's a lot of atoms there. It also starts to make it not as clear what that thing actually looks like. Whereas if we look down here, you can really see the structure. You can see the shapes of how this thing works. Later in the semester, we're going to compare different classes of antibiotics, and you'll see that structurally, the class of antibiotics called penicillins, as well as cephalosporins, all have the same kind of a core, the same kind of a thing in the middle that actually makes them do what they want to do. So using line structures is a nice way of really expressing the structure of a molecule. Okay, one thing we haven't dealt with yet with these line structures is when we don't have carbons. If you look at the structure of amoxicillin, you'll notice that these OH, NH2 type things on the ends, those are hydrogens. So the hydrogens are there, they are shown. And that's actually really important. Only carbons get their hydrogens taken away. Everything else, the hydrogens stay there. So let's pull up an example here and show how we would make a structure for one that's a little bit more complicated than what we've seen so far. All right, so here's our Lewis structure, and there's a lot going on here, right? You've got you've got some C's, some O's, all kinds of stuff, some triple bond, a double bond. It's a big thing. All right, so let's go through this and kind of do this step by step. So first of all, one thing you'll see in this particular book is they always have these dots around oxygens and nitrogens. Those are called lone pairs or non-bonding pairs of electrons. If we get into electron structure later, we'll kind of talk about what that means. For now, you can just really ignore them. You can either leave them as is, or you can just get rid of them. When you're actually looking at organic chemistry and reactions in organic chemistry, those become really important. We're not going to get into that so much this semester. So you can leave them or you can take them out, either way. But what we are going to do to make this a little easier on ourselves is we're going to first draw a condensed structure so we can see how the carbons and everything else connects to each other without all these extra hydrogens everywhere. So all I'm going to do is go through the structure, draw it exactly as it is here, but just condense the hydrogens onto their carbons. So instead of the H and then a line and then O, I'm just going to call that HO. Down here, I've got CH2. Also should note, it doesn't really matter whether you put the H on one side or the other of an atom. Sometimes people like to, like for this one, make it H2C, so it's very clear that the carbons are connecting to each other and not the hydrogens. But again, if we know, as long as we know that hydrogens always have to be on the outside, it's okay to draw it that way, as long as we're communicating to other people who also know that. So we've got CH2, then we've got another CH2 here, then we've got that O, then we've got another CH2, then we have a C triple bond to C, and then a CH, then a double bond, another C here, CH3, whoops, you can't even see it here. And then down here is the last CH3. Okay, so we can already see, even though it's still a pretty big molecule, at least it kind of makes a little bit more sense now. We've got this chain that goes along this way and then branches out at the end. Single bonds between carbon atoms or carbon and oxygen can rotate. So we can make those any angle, any direction we want. Double bonds and triple bonds don't rotate. So we have to actually keep the geometry or the orientation that we find for those. So what I'm going to do here is just number my carbons. 1, 2, 3, 4, 5, 6, 7. Just to keep track of everything. And you could number the oxygens too if you want. Nothing wrong with that. But just however you want to keep track of it. We just don't want to lose atoms along the way. So now when we want to draw a line structure, I'm going to start over at this HO again. And because oxygen is not carbon, remember, we can't get rid of that hydrogen. We only get rid of the hydrogens when they're on carbon. So that stays as it is. And then we're going to start counting off with what we've drawn here. So we've got HO that's going to go kind of zigzag down to carbon 1, and then up to carbon 2. And then carbon 2 is connected to an oxygen. So we're just going to put that there. Then we'll go over to carbon 3. Then to carbon 4. Then the triple bond. Now triple bonds are actually linear, which means they don't bend. So I'm going to keep that in a line. If you zigzag up with your triple bond, that's fine. I don't have a problem with that. But just because that's how it actually goes, I always keep these straight. So there's carbon 4 and 5. Then we've got number 6. Then we can zigzag up to number 7 with a double bond. And then 8 and 9 are both going to be coming off of number 7. So again, let's put our numbers in here so we can see how everything worked out. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a line structure for this compound. So last step then is just to check everything. Do I have everything connected properly? So I would go back to the beginning of the structure and say, all right, is carbon 1 connected to carbon 2? Yep. Then I've got the O, then I've got 3, then 4. 4 is triple bonded to 5. So I've got 3 lines there. Then I go to 6, 5 and 6 connected. Then between 6 and 7, I've got a double bond. Great. Then I've got 8 and 9 both coming off of 7 or both connected to 7. So that works. So that's good. Now, in terms of angles, are there other ways you could do this? Yes, and they would also be correct. So for example, let's say we kind of did everything the same, but down here, when we got to that double bond, we decided to go down instead of up. No problem. That's actually the same structure. That works great. So we can do that. Same thing over here. What if we wanted to start the OH down and then go up from there? We can do that as well. So it's not that difficult. It's just something you have to kind of go step by step and make sure you're keeping track of everything. All right, for the last example, I want to take one of these from the homework that is a little bit more difficult way of dealing with these parentheses. I guess not difficult, but let's take a look. We're going to look at F here, over here, which I'm going to draw out. It's CH3, CH2, free COH. That's F. Okay. How do we deal with this? We've got all this stuff in parentheses with a 3, so that's going to be taken 3 times, and then this C and OH. Now, when we're dealing with these parentheses, remember from our example above, it doesn't mean that those are connected next to each other, because that we know that can't work. Any CH3 always has to be at an end, because if it's CH3, there's only one more spot on that carbon to get a bond. Only 4 bonds total. So this tells us if there's a CH3 in parentheses, that tells us that there actually has to be multiple of this whole group. All right, so this isn't CH3, CH2, and then another CH3, and another CH2, and another CH3, and another CH2. This is CH3, CH2, CH3, CH2, CH3, CH2, all connected to this carbon over here. All right, so when you're doing these problems, that whole block of problems in the homework, the first step is always to make the condensed structure and then get to the line structure from there. So for the condensed structure, remember, I want to really see all of this connected. So CH3, CH2, I'm going to expand a little bit like that, because that's what that is. And then there's 3 of them. So I'm just going to write 3 of them. Okay. And then I know carbon has to have 4 bonds. So these carbons have 4 bonds, 3 to hydrogen and 1 to the carbon. These carbons over here only have 2. So each one of these is going to need to get 1 more bond. And that's connected to this carbon here. Okay, it looks a little weird because I had it all spread out, but we can condense it more when we make our line structure. And then the rest of it is just the O and the H. And since it's a condensed structure, actually, I'm just going to keep it OH. And then before you go on, or before you say that that's good, remember we want to make sure that all of our atoms are accounted for. Looks like they are. And we want to check those bonds again. So we want to make sure that the carbons all have 4 bonds. Like this carbon has 1, 2, 3, 4. Yep. Oxygen has 2. Hydrogens have 1. That all looks good. If we had done something different here, like if we had put all those CH3, CH2s in a row, then not only would those CH3s have been kind of messed up, but we also would have messed up this carbon here. That wouldn't have worked either. So if you check all the bonds and make sure everything has 4 bonds, that's a good way of making sure that you actually have drawn the right structure. So now when we convert this to a line structure, at least we have an idea of how this thing could be connected. And there's lots of different possibilities. So you could kind of start from here and like make your way down around this way and say that this is a 5 carbon chain, and then these are connected out of the middle. You could kind of leave this intact. We can maybe start from this one. Let's do that. Because this is this kind of center of it, it almost seems like it makes more sense here to start from that one and branch everything out from there. So when I draw my line structure, again, there's lots of different ways to do it. As long as everything's connected properly and all the atoms are accounted for, it's fine. It doesn't have to look exactly like mine. But I'm going to start from this carbon and the OH, just because I feel like that's like the easy part to draw, and this stuff is where it gets a little bit more complicated. So there's my carbon, we'll call that carbon 1. And then we'll go back from here. We'll go 2, 3, 4, 5, 6, 7. Again, totally arbitrary. You can number however you want. I'm just trying to keep track of everything. So here's my carbon 1 right there. And then I can think about what's connected from there. So coming off of carbon 1, I've got like 2 carbons going up I can think about, and 2 going to the left, and 2 going down. So I've got carbon 2 and 3 up here. And again, I could have made that to the right. I could have made it to the left, whatever. I've got carbons 4 and 5 down here. And then I've got carbons 6 and 7 down here. Again, you can kind of draw that however you want in terms of the angles, but the most important thing is to get everything connected. Notice that the H is still there connected to the oxygen. That's important because we want to make sure that only the carbons, the hydrogens on the carbons get abbreviated. And then the other stuff is all there. We've got our atoms, and yeah. So I think we're good. So there's our line structure. All right, so that's this part of the work for this module. Start working through those. And then on Monday, we're going to talk more about how these molecules interact with each other and how we can, how they attract each other and the attractive forces, and how we can judge the strength of those attractive forces through the types of bonds and the types of atoms that are in there. All right, so hopefully this goes okay for you. Let me know if you have questions or if you have trouble going through this over the weekend. And otherwise, I will see you on Monday. Thanks, everybody. Hope this goes okay.